Okay, so now we're going to take a few minutes and talk about how might you suspect that pH might be related to Ka and percent ionization. So eventually we want to take a look at and see how pH and Ka are related to each other so that we can calculate pH of various acid and base solutions. Okay, so how might you suspect pH is related to acid strength, particularly looking at how do you think pH is related to Ka, if we have the Ka number? How do you think pH is related to percent ionization? So if we just kind of work through some of this information that we already know, we can kind of already make some correlations, right? So Ka, if we have a high Ka number, that means the acid has dissociated a lot, and that means we have a stronger type of acid. We have a higher Ka number, we have a higher percent of acid that's dissociating, we have a larger amount of H plus ions or H3O plus ions that are being formed. Therefore, the more H plus ions is the acid, then we would suspect that the pH would be acidic. And on the pH scale, acidic is a low pH number, less than 7 is neutral. So 7 is neutral, less than 7 is acidic, above 7 is basic. So if we have a stronger acid, then that means that the Ka should be a higher number because we're dissociating. The acid is dissociating more to give us a higher Ka number, and the percent of acid ionizing and dissociating is also higher. So we're making more H plus ions or H3O plus ions if we're showing that with water in the equilibrium reaction equation. That will be a high amount of those concentrations, okay? And the pH will be acidic. That will be a low number. Okay. If we have a stronger type of base, same thing, base dissociating, we're going to have a high Kb number, a high percent of ionization of that base dissociating. We're forming OH minus ions on the product side, so the concentration hydroxide will be high, and the pH will be basic, so that would be greater than 7 number. It should be a higher pH number that we would calculate. In terms of weaker acid, okay, so a weak acid is not dissociating very much, so we would have a low Ka number and a low percent ionization number. Depending on what the concentration of the acid is will dictate more closely what the actual pH number is, but we do know that the concentrations of the H plus or H3O plus concentration will be low, okay, and the pH will be more basic. It might not actually be above 7, but it will be a higher pH than a typical stronger type of acid, we should say, okay? And we have a weaker base. We'll have a lower Kb, and we also have a lower percent ionization, and the OH minus ions, we have not dissociated very much base, so we have a low amount of hydroxide ions, will be low, and then the pH would be more acidic. Again, it might not be below 7 number that we calculate, but it will be a lot lower, more acidic than other stronger bases that we would see. Okay? Okay, so eventually we're going to get to the point where we can look at an equation that relates Ka to pH. Okay, but before we can talk about pH, we also need to talk a little bit more in detail about something called the self-ionization of water. Okay, and so water itself actually can react. One water molecule can react with another water molecule, and one can act as an acid and one can act as a base, and then they can form H3O plus and OH minus ions respectively, just between two water molecules. Okay, but one question that we think about is, does pure water conduct electricity? So if they can react with each other, one water molecule with another, and form H3O plus and OH minus ions, then they're forming ions in solution. So why doesn't water conduct electricity? So it does not conduct electricity, right? It's actually considered a non-electrolyte, which means it doesn't conduct electricity. And even though it forms ions, it's a very weak, very weak electrolyte. So even though water can act as, remember that term, amphoteric species, meaning that it can act as either an acid or base, okay, with itself, one can be an acid, one can be a base, and it's forming, and they're swapping hydrogens, okay? So we have H3O plus and OH minus ion forming over there. One water molecule takes a proton, the other gives it, and then you have the respective ones over here. Okay, so if we kind of go through this analysis here, we have equilibrium that's occurring because they can redissociate and form back into the water molecules. Okay, so we can write a K for this reaction, concentration of products over reactants, concentration of products over reactants. The water molecule is pure liquid, and that gets squared because there's two of them. Right, but remember that the pure liquid is the concentration of 55.56 molar. I do apologize for the sun's shining in the window right now. I can't get my blind down far enough to get that glare off the board. All right, but remember that this water, liquid water, is 55.56. And so if we multiply that term over here to the Kc side, now that Kc then turns into what we call Kw. And so this is the dissociation of water molecule, Kw for water. Okay, and when we do that, we just have concentration of H3O plus and OH minus, because this all down here is over 1, so there's nothing down here we need to show. All right, and this is actually calculated to be 1 times 10 to the minus 14th. This is an extremely small number, 0.13 zeros and then a 1, right? A very, very small number. So that tells us that this does occur, and it is significant enough in terms of calculating pH and understanding the concentrations of H3O plus and OH minus. However, the amount that we actually form is really, really small amount. And so we have such small concentrations of these ions in here, and it's not actually enough ions in solution to conduct electricity. However, in biological systems, for example, when we're looking at concentrations of H3O plus and OH minus ions, those concentrations are really, really, really small. And so this process becomes significant in examples that the concentrations of H3O plus and OH minus are also really, really small. And so you also actually have to take account into your calculations for this particular effect and process that's occurring. Okay, so remember the flow chart that I gave you when we look at equilibrium type problems, right? The first thing we need to determine is what is strong and what is weak, and then we would solve the equations accordingly, right? So if we have a weak acid or weak base, then we have an equilibrium, and we would have to solve the problem with an ice table accordingly and answer whatever's being asked in the problem. So I want you to think about that when we just take a look at this question here. It says, what is the H3O plus concentration and hydroxide ion concentration in pure water? So we just looked at self-ionization of water. And if I want to calculate what the concentration of each of the H3O plus and the OH minus ion species are, then I have an equilibrium going on because it's weak, and I can solve it using an ice table. Okay? So remember that pure solids and pure liquids, they do not appear in the equilibrium constant. Right? And we also know that this Kw number is equal to 1 times 10 to the minus 14th, and that was at 25 degrees C. Okay? But here we do not include the pure liquids, so we can just omit those in our ice table. This is 0 to begin with, and then we have some amount, X, that is forming, 1 mole of each. And so down here in my Kw, I can put X times X, which is just X squared. Right? And then how do I solve that? I just take the square root of both sides, and that gives me X is equal to 1 times 10 to the minus 7th, and I'm going to put that back in for molarity because our concentration of water is in molarity, and that's how we would solve the concentration of the H3O plus and the OH minus ions. Okay, so we just calculated the concentration of H3O plus and OH minus ions in pure water using Kw, which is a constant at 1 times 10 to the minus 14th. And we did an ice table and we solved that those concentrations are both equal to 1 times 10 to the minus 7th in pure water. So equal amounts in pure water, and that's their concentration. Okay, so I just want to take a minute and conceptually and visually think about what do those number level concentration numbers mean in conditions of acidic, neutral, and basic. So what I have done here is I want to visually look at what those concentrations look like at various pHs. So over here I've plotted the concentration of H3O plus or OH minus ion. It can range anywhere from 1 all the way up to 1 times 10 to the minus 14th, which is the Kw of water. And in pure water, we know that we have equal amounts of H3O plus and OH minus ion, okay? Which if we take a look here at this scenario, it's a neutral condition, okay, at pH 7. And so on the x-axis, I've plotted pH. So I have acidic, neutral, and basic conditions here, okay? So in neutral conditions, pH 7, and the pH scale goes from 0 to 14, okay, so 7 being right in the middle. And I have equal amounts of H3O plus and OH minus ion 1 times 10 to the minus 7th. If I'm in acidic conditions, then I have a lot of H3O plus concentration. And so that means the number I calculate for H3O plus should be a higher number than 1 times 10 to the minus 7th. So on my bar graph here, I'm going to have a lot of H plus ions or H3O plus ions for acidic conditions. So I'm going to be over that kind of cutoff equal point here. And I'm only going to have a small amount of basic ions. Okay, so I'm not going to have none, but I'm going to have, just a teeny tiny amount, okay, depending on the concentration of the acid or base. Okay, and then for basic conditions, right, the ion that describes bases is the hydroxide ion. So I'm going to have a lot of hydroxide ion with respect to that equal ratio amount here, and I'm only going to have a really small amount of the H3O plus ion there. Okay, so that's kind of like what it looks like. You're kind of, if you have more than one, more than the other, then it's going to acidic basic. If you're kind of about the same, then you're at neutral pH conditions. Okay, so just take a few minutes and we're going to go through each of these examples here. I'm going to identify under each of these different conditions, is that solution acidic, basic, or neutral? And this is just a short little exercise that really just gets you to think about the exponents and what that number means. So I like to compare each number to the neutral conditions, 1 times 10 to the minus 7th. If the concentration is a higher number than 1 times 10 to the minus 7th, then I have more of that ion present, the number is larger, then that means it'll be easier to dictate what condition is present at the solution. All right, so in A here we have hydroxide ion is 1 times 10 to the minus 5th. That number to the minus 5th is a larger number than neutral conditions at 1 times 10 to the minus 7th. So this is greater than, so I have a larger amount of hydroxide ion at neutral condition than I do at just compared to this number. So that means that the hydroxide ion is in greater amount, that is a base. So this is more basic, and the pH should be a number that is greater than 7. Okay, so I would be in this scenario here for the A. All right, so for B, we're looking at H3O plus is 3.8 times 10 to the minus 9th. So this number is smaller than 1 times 10 to the minus 7th. So it's less than, why is that not writing out very well? Okay. This number is less than. So I have a smaller amount of hydronium ions. Okay, so I don't have very much hydronium at all, which means that the solution is this scenario again, basic. And that would give me a number that is larger than 7 if I were to calculate the pH out for that. C is H3O plus ion. Concentration is 6.2 times 10 to the minus third. This is a much larger number than times 10 to the minus seventh. And so this number is corresponding to the acid concentration, the H3O plus concentration. So I have a lot of H3O plus concentration for this C example. So I am in acidic conditions. And the pH should be less than 7. It should be a small number. Okay? And then our last one here, we have hydroxide ion concentration is equal to 4.5 times 10 to the 10th. This number is a smaller number than this times 10 to the 7th, so it's less than. This concentration is relating back to the hydroxide ion concentration, and that means I have a small amount of hydroxide here. So I have a small amount of hydroxide, which means I'm going to have more acid, and I'm in the acidic conditions here. And the pH should be less than 7 again. Okay? Okay, so now we're going to talk about how do we calculate pH and pOH. Okay? Eventually getting up to the derivation of it. Okay? So first I just want to point out the handout that I gave you, the flow chart. We're kind of going to be starting to develop and get all of these different equations that we're going to put in our toolbox so that we will be able to solve equilibrium problems involving weak acids and weak bases. Okay? All right, so we're still talking, getting into pH, and pH is used to express the concentrations of H plus in terms of integers, so whole numbers, some with decimals, rather than the really, really low H plus concentrations, 1 times 10 to the minus 10, 1 times 10 to the minus, 8th, 1 times 10 to the minus 14th. Concentrations that they are. Particularly in biological systems, they're really, really low concentrations. Okay, so expressing the concentration of H plus in terms of pH is strictly just for convenience. Okay, it's just a way that the reason why we express things in scientific notation or in exponential with exponents is just to make the number a little bit more easy to work with sometimes. This was first introduced by Sorensen, and it's referred to as the power of hydrogen. So the pH, the P stands for power, and we're looking at the H plus concentration. Okay, and the way that we calculate that is pH is equal to the negative log of H plus concentration, or this also can be substituted as H3O plus. All right, and then if you take the inverse log of that, here, you can then calculate the H plus concentration if you know the pH. And so when we do that, if we know the H plus concentration, we can take the 10 to the negative pH number to get the H plus concentration. So if you're trying to solve for pH, you would use this equation and plug in H plus. If you're trying to solve for H plus concentration, you would use this equation and plug in the pH here to solve for that. All right, we also can correlate the same equation into terms of pOH. So we can just substitute hydroxide ion concentration the same way we would for H plus concentration, and we can solve negative log of hydroxide ion concentration will give us a pOH. That would be the power of hydroxide ion. And the same way we can calculate hydroxide ion concentration if we know this pOH value using that equation there. Okay, so just an example here, H plus concentration is 1.0 times 10 to the minus third molarity. Calculate the pH. So pH is equal to negative log of 1.0 times 10 to the minus third is equal to negative, from the negative there, log of 1 times 10 to the minus third is minus 3. And the negatives negate and give us 3.00 for a pH. Just a note about logs for scientific notation and for how many decimal places we should record. The number of digits in a log number corresponds to the number of decimal places that you would record on the pH. So only the number to the right of the decimal place are the significant numbers in a log function. Okay? Another thing that is interesting and easy to kind of see the correlation for properties of logs, if it's 1 times 10 to the minus 7th has a pH of 7. 1 times 10 to the minus 10th has a pH of 10. Here, 1 times 10 to the minus 3rd has a pH of 3. So if this is 1 here as the concentration, whatever the exponent is the pH number. So that's kind of a little trick that when you calculate, you know it should be at least around that number, even if this number here is not 1. Okay, so we're going to do another example calculating pH and POH. So in this example here, we have H3O plus concentration is 1 times 10 to the minus 7th. And I've just gone ahead just because the question doesn't ask, but I went ahead and just calculated the pH of it. Okay, so the negative log of the H plus concentration gives me a pH of 7.00, sorry. All right, so the question says, calculate the hydroxide ion concentration from that information, right? And so thus far, we know that the correlation between H plus concentration and OH minus concentration that we have so far is the KW equation, right? And so we know that KW is equal to this number here, and we know that, so we can solve easily for OH minus concentration. All right, so that's the equation that you want to use if you're given H3O plus concentration and it says to calculate hydroxide ion concentration. All right, so we're going to use the KOH equation, which is this one here. We know this, we're solving for this. So we're just going to rearrange the equation, divide this over here to get OH hydroxide ion concentration equal to this. And this is given hydroxide ion concentration, or excuse me, the hydronium ion concentration 1 times 10 to the minus 7th. So I plug that in there. And when we divide exponents, we just subtract them, and we get hydroxide ion concentration is 1 times 10 to the minus 7th. Okay, so that's pretty easy and straightforward. The second part of the question, it says calculate the POH. Right? So now that we have the hydroxide ion concentration, then we can use the POH equation. All right, again, in our toolbox, we're developing and kind of summarizing and putting together lots of these equations that we have, and we can pull from any of these eventually to solve our ice table problems. But first, we're just practicing each equation individually, okay? All right, so calculate POH, so we can use the POH equation here, and then I'm just going to plug that right in, and I get 7.00. Right? An interesting thing to think is in a previous problem, we calculated the concentration of H3O plus and OH minus in pure water, right? And we used the KW to calculate that. And the concentrations that we got in pure water for H3O plus and OH minus are 1 times 10 to the minus 7th, right? So this is where we're starting at here, 1 times 10 to the minus 7th. And we calculated this 1 times 10 to the minus 7th. So this is in pure water. And the pH of this is pH 7. Therefore, the POH should also be 7 because we're neutral conditions, right? So that's just something that I went ahead and calculated pH there to show you that we're at pH 7, neutral, equal amounts of each of the species. And then you get a pH that's 7, and you get a POH that's equal to 7. So here shortly we're going to see an equation that relates POH and pH together, okay? But first let's do another example calculation. So here we're given pH is equal to 5. Let's calculate the hydroxide ion concentration and the hydronium ion concentration, okay? All right, so I know the pH and I want to calculate H3O plus. All right, so pH, H3O plus, I'm going to use this equation here. I know the pH, I want to solve for this. So I can just plug in 5 right into pH, and that gives me 1 times 10 to the minus 5th, all right, for the hydronium ion concentration. All right, the next part of the question says calculate hydroxide ion concentration, right? So just like we saw up here, okay, we know the H3O plus concentration, and we want to solve hydroxide ion. So we can use Kw. Kw, right, is equal to this up here, right? So again, we know this, we want to solve for this. And so I'm just going to plug in my hydroxide ion concentration like I did right there. And that's equal to 1 times 10 to the minus 14th. And I can rearrange the equation for the hydroxide. So I'm going to divide this over 14 minus 5, because we will be dividing those two numbers. We subtract the exponents, gives us 1.0 times 10 to the minus 9th for the hydroxide ion concentration. Okay, so as we are developing how Ka is related to pH, first I want to recall what Kw is equal to. So Kw is equal to the H3O plus concentration times the hydroxide concentration is equal to 1.0 times 10 to the minus 14th. And if we just do a little derivation of this to get to the relationship between how Ka and pH is related to each other, we take the log of both sides of this equation and this equation. When you multiply two things and you take the log of them, you add them. So the log of H3O plus the log of OH minus concentration is equal to the log of 1.0 times 10 to the minus 14th. Okay? This looks very similar to the pH equation, except it doesn't have the minus sign there. So I'm just going to put minus pH is equal to that. And this would be the same thing, minus POH is equal to that, because we're missing the minus sign there, so we put the minus sign there. And the same thing, the minus sign is missing, but this number here is equal to minus 14 then. Okay, and so all I'm going to do next is if I just multiply by a negative all the way through, then the negatives will all negate each other, and I will end up with pH plus POH is equal to 14. So in our previous example problems, we were calculating pH and POH. When you add those two numbers together for a particular solution, they should equal 14. So if you know one of these or the other and you're asked to calculate the other one, then you just can take 14 minus that pH or the POH to get the respective value. Okay? Okay, so just like we use pH to explain or represent H3O plus concentrations just for convenience only, using the P scale, okay, we can do the same type of calculation for Ka and Kb numbers. So Ka, equilibrium dissociation constant of an acid, and Kb, equilibrium dissociation constant of a base, are usually pretty small numbers when we're looking at least in biological systems. If we're looking at a weak acid or a weak base, we also are looking at really small Ka and Kb values. So 1 times 10 to the minus some large number in the exponent, which gives us many, many, many decimal places. So it's a really small number. So again, we can just use that same calculation. Instead of pH, we can do pKa, negative log of Ka, and then just represent that in a larger number as an integer. Okay, and the same thing for Kb, we can do pKb is equal to negative log of Kb, and the same thing. So since the equations are pretty similar, we also can think in terms of what they mean. If we have a Ka that is a really small number, so Ka, we're looking at an acid that has not dissociated very much, does not make very much H plus ions, right? So the Ka number will be very small, right? It'll be very small, and the pH of the solution will not be very acidic. So the pH will be higher. And if I take the pKa of the Ka, then if I have a small Ka, then I will get a larger pKa. And so that kind of correlates. If I have a small Ka and it's a weak acid, it will not have a low pH, it will have a higher pH. And the pKa will be a higher number than the low Ka, and that higher number is kind of indicative of a higher pH number, because it'll be kind of more basic, it'll be less acid in there really. Okay? So the higher the Ka, the lower the pKa. So they're kind of inversely related here. The lower the pKa, I kind of correlate that to pH. The lower the pH as well, the stronger the acid is. The higher the Ka, the more the acid has dissociated and ionized, the stronger the acid is. Okay, so here we can see is if the Ka is 1 times 10 to the minus 2, this is pretty high concentration on the Kw scale, anywhere from 1 times 10 to the minus to 1 times 10 to the minus 14th. This is on the higher end scale of the number, and so a higher Ka, when I calculate that, gives me a low pH number, and that means that the acid is pretty acidic. Okay, and a lower Ka, we have a higher pKa, and the weaker the acid is as well. Okay. The same trend is true for KBs. So the higher the KB, the lower the pKb, the weaker the base is, and the lower the KB, the higher the pKb, the stronger the base is. One last relationship that I wanted to bring to your attention, and this will complete all of our equations that are in our toolbox for the flowchart I gave you. The relationship between Kw, Ka, and Kb is such that Kw is equal to Ka times Kb, and we know what Kw is equal to. It's equal to 1 times 10 to the minus 14th, and it's also equal to H3O plus times OH minus concentration. And so you can probably see that a little bit more clearly on this handout here. So it's the first two equations. Kw is equal to Kh times Kb times 1 times 10 to the minus 14th, and then Kw also is equal to this. So you can combine both of these two equations to solve for any of those variables that you might need in a problem to solve it. Okay, so now we have completed and worked through at this point in the lecture all of the equations in our toolbox, and the next thing that we're going to take a look at is solving different types of problems that are strong or weak acids and bases, and calculating pH. We could be calculating Ka. We could be calculating any of these types of variables here in the problems and just pulling what we need from our toolbox to solve them. Okay. Okay, so now we're ready to get into calculating strong acids, strong bases, weak acids, weak bases, and the way that we're going to do that is use our handy dandy flowchart. All right, so anytime we have a question that says calculate pH, calculate concentration of H3O plus or OH minus concentration, calculate Ka, calculate Kb, we're going to pull the flowchart out, okay, at least initially till you get used to it. Solving these types of problems. Okay, and so the first thing that you always want to identify at the top of our flowchart is it strong or weak? Okay, depending on if it's strong or weak will determine how you solve the problem. Okay, if it is a strong acid or base, then we have 100% dissociation. Okay, 100% of it is dissociating, and we can go ahead and write the reaction equation. First we would have to identify if it's strong or weak, right? 6 strong acids, and then the bases are column 1, column 2, starting with calcium paired with hydroxides, and then we would solve it accordingly, okay? So because it's 100% dissociation, we already know how much has dissociated. It's 100%. So whatever the concentration is of the acid or the base given, then we already know these concentrations, right? And so then we can just plug them directly into a pH equation or pOH equation, okay, or one of these over here, solving for whatever is being asked in the problem, okay? If it is not one of the 6 strong acids or one of the bases, strong bases, then you're going to solve it as a weak substance. Okay, the first thing that you want to do is write the equilibrium equation. And because there's an equilibrium going on, we don't know how much has dissociated. So we're given a certain concentration of the acid or base. We don't know how much H plus is forming. We don't know how much OH minus ion is forming. And the only way that we can figure that out, right, is to solve those concentrations using an ice table, which would be solving concentration of them at equilibrium. And then once we've solved for those concentrations of what they are at equilibrium, then we can just use the toolbox and plug them into any of these equations and solve for whatever the problem is asking. Okay, so first we're going to take a look at some examples that are strong All right. And of course you would have to identify that it's strong, because it's not just going to say on an exam or homework question, this is a strong acid or strong base, solve it this way. Okay, so the first question here says, what is the concentration of H3O plus and what is the concentration of hydroxide ion in a 0.25 molar solution of, and the word might be written out for the chemical compound. It might say barium hydroxide. So if this is barium hydroxide, then you would also have to write the formula for that before you would solve it. Okay, so barium hydroxide, and you would think, oh, it's a hydroxide, and oh, it's barium, right? So column 1, column 2 starting with calcium and below, because these two up here are not soluble very much in aqueous solutions, so they don't dissociate completely. So calcium and below, oh, there's barium. Barium paired with hydroxide, that is definition of one of the strong bases. So barium hydroxide, we're going to write the reaction equation, is going to 100% dissociate into its ionic form into barium plus 2 ion, because it's column 2, okay, plus 2 moles of hydroxide. So hydroxide is -1 polyatomic ion. We have to have 2 of them paired with 1 barium. So we have 2 moles of hydroxide there. Okay? So the concentration of barium is 0.25 molar. However, it's 100% dissociated. So there is none left over here. So this really essentially goes to 0. Okay, so this is 0, and we have 0.25 of barium and 2 moles of 0.25 of hydroxide. Okay? So it's kind of like an ice table we are setting up here, except we don't have to go to equilibrium because it's already just over here, okay? But we do have 2 moles of that specific concentration given, okay? So the concentration of hydroxide ion is 2 times the given concentration of barium hydroxide, which is going to equal 0.50 molar. So there's our hydroxide we calculated. And then we know hydroxide, we can use the Kw equation to calculate the H3O plus concentration. So Kw there, hydroxide I've just solved for, and I can calculate H3O plus concentration. From that, I might also be asked to calculate pH. So pH equation, I know the H3O plus equation, so I can just plug that right into the minus log equation and get my pH value there. Okay. Another example here, calculate each of those concentrations again in a 0.040 molar solution of HNO3. So HNO3 we want to recognize, is it strong or weak? This one is nitric acid. It is one of the 6 strong acids. So we'll write the equation. 100% has dissociated into its ionic form. And this essentially is 0, so there's nothing here. We have 0.040 molar of H+, 0.040 molar of the nitrate anion, and we're calculating the concentration of each of these. So the H+ ion is the H3O plus concentration. Here it's just not showing with water reacting with it, so that is 0.040 molar. And then how do I calculate hydroxide ion concentration? Again, I can use Kw, right? So Kw over the H3O plus, plug that in, and you get this concentration for the hydroxide ion. If you're then also asked to calculate pH, right? Here's the H+ concentration. I plug that into the pH equation and solve for pH. Okay? So first thing you want to do, identify if it is strong or weak and solve accordingly. These were some examples looking at strong base, strong acids.